Welcome to the LFCA exam preparation journey, where we will systematically build the technical foundation necessary to achieve your certification goal. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to the Linux Foundation. All trademarks belong to their respective owners. In this course, we will dissect the core requirements for the Linux Foundation Certified IT Associate, an entry-level credential designed to validate your knowledge of foundational IT technologies. This certification is a strategic stepping stone for professionals aiming to enter career paths in system administration, cloud engineering, or DevOps. By mastering these basics, you demonstrate a standard of competency that is respected across the global open source community. Our approach involves balancing theoretical knowledge with practical application in simulated environments, ensuring that you are not just memorizing answers, but truly understanding the technology stack. You will gain clarity on how Linux functions at its core, how it lives within the modern cloud, and how to secure those systems against common threats. The curriculum is structured into 6 comprehensive chapters that align directly with the LFCA exam objectives, starting from Linux fundamentals and moving through to system administration, cloud computing, networking, and security. We will explore how operating systems manage resources, how software packages are maintained, and how the networking protocols that power the internet actually operate. Each topic is chosen to provide a realistic view of what you will encounter in professional environments, whether you are managing a physical server or orchestrating infrastructure in the cloud. We will also touch upon software development lifecycle basics to ensure you grasp how these technical domains interconnect in modern deployment pipelines. This is about professional growth, providing you with a roadmap that turns abstract concepts into actionable technical skills. Before we dive into the technical details, you should consider setting up your own lab environment, as hands-on interaction is the most efficient way to learn Linux. You can achieve this easily by leveraging virtualization software on your local machine or spinning up inexpensive cloud instances from major providers. This practice allows you to experiment with system commands without the risk of breaking critical infrastructure, which is a vital part of your learning cycle. Throughout this course, I encourage you to pause, recreate the examples provided, and vary the inputs to see how the system responds. By actively engaging with the terminal, you will build the muscle memory required to navigate and troubleshoot systems under pressure during your certification exam. Understanding the exam structure is essential, as the LFCA is weighted across distinct domains, each requiring a different level of attention. Linux fundamentals naturally command a significant portion of the focus because they underpin almost everything else we will discuss in the later chapters. We will track your progress through these domains to ensure you are meeting the expectations set by the Linux Foundation for entry-level candidates. Your success will depend on your ability to synthesize this information and apply it to the specific scenarios presented in the exam. I am here to guide you through this process, simplifying the complexities of the current IT landscape into manageable, logical pieces. Prepare yourself for a thorough exploration of modern professional IT standards. See you in the next session. Welcome to this chapter on the Linux file system, where we will examine the structure that governs how your operating system organizes and accesses data. Mastering these directories is essential for any professional working with Linux systems. In this chapter, we will demystify the Linux file system hierarchy standard, commonly referred to as the FHS. Understanding where files live is not just a matter of convenience, it is a fundamental requirement for troubleshooting, security, and administrative maintenance. The FHS provides a consistent structure across distributions, ensuring that if you learn the layout here, you can find your way around almost any Linux environment. We will break down the root directory and explain the specific purpose of each subdirectory found under the top-level slash. This structured approach prevents chaos by dictating exactly where configuration files, binaries, libraries, and temporal data reside. By the end of this discussion, you will understand the clear distinction between static files that remain largely unchanged and variable files, such as logs or temporary data, that fluctuate during normal system operation. The root directory, denoted by a /, is the starting point for every file and folder in the system. Everything begins here, regardless of which physical storage device holds the data. Directly under root, we find essential directories like /bin and /bin. The /bin directory houses binary executables required for essential user commands, while /bin holds binaries primarily used by the system administrator for maintenance tasks. You will also find the boot directory, which contains the files necessary for the kernel to load and the bootloader to execute. In contrast, the /dev directory acts as a special interface, containing device nodes that represent physical or virtual hardware components. Each of your hard drives, terminals, and even null devices appears here because, in the Linux philosophy, almost everything is represented as a file. Moving deeper into the hierarchy, we encounter /etc/home and /root. The etc. directory is perhaps the most critical for administrators, as it holds the strictly static configuration files for the system and installed applications. You should never store user data here, as this directory is reserved for configuration logic. The home directory, conversely, is where individual user profiles reside, providing a dedicated space for personal documents, settings, and desktop data. The /root directory serves as the home folder specifically for the superuser, keeping administrative files isolated from normal user accounts. Keeping these locations distinct ensures that a user's accidental file deletion cannot compromise system-wide configuration files or critical administrative scripts. We also have directories designed for libraries, mounting, and optional software. The lib directory contains shared libraries necessary for the binaries located in /bin to function correctly. When you install third-party applications outside of the package manager, the mount EOT directory is the standard location for these locally installed software packages. For hardware peripherals, we use /media and EMNT. The /media directory is typically used for mounting removable media like USB drives or optical discs, while /MNT is traditionally reserved for manual, temporary mounting of file systems by an administrator. This separation allows the system to manage its own resources while providing you with clean, predictable touchpoints for accessing additional storage or external devices. Finally, we must address the directories that handle volatile and user-specific data. The /tmp directory is intended for temporary files that any user or application might need to create and subsequently delete. It is designed to be cleared periodically by the system, so you should never count on finding persistent data there. The ESR and /var directories offer a contrast in utility that is often misunderstood by beginners. The ESR hierarchy contains most of the user-facing binaries and documentation that are considered shareable and static, including the ESR local path for software installed locally by an admin. This /var directory, however, is reserved for variable files, which include system logs, spool files, and databases that grow and change in size as the system runs. Understanding this nuance between static SSR content and variable /var content is a cornerstone of effective Linux system management and performance tuning. See you in the next lecture. Hello, welcome back. Today, we turn our attention to the fundamental task of navigating the Linux file system through the command line interface, a skill that is non-negotiable for system administration. When you first interact with a Linux terminal, you are interacting with a shell, which serves as an interface between you and the underlying operating system kernel. Understanding the structure of a command is vital, as every instruction follows a predictable format consisting of the command itself, followed by options and arguments. The command is the program you wish to execute, while options, typically denoted by a hyphen or double hyphen, modify the behavior of that command. Arguments represent the specific targets of your command, such as a file name or a directory path. Your shell interprets these strings by scanning the system path for the executable and then expanding wildcards or environment variables before passing the final data to the process. This rigorous structure ensures that the system understands your intent, whether you are simply viewing file metadata or performing complex administrative tasks deep within the directory hierarchy. By mastering this syntax, you remove the guesswork from your daily terminal interactions and begin to treat the command line as a precise tool rather than a cryptic mystery. To orient yourself, the first command you will likely employ is pwd, which stands for Print Working Directory. This command outputs the absolute path of the directory you are currently inhabiting, starting from the root directory, denoted by a /. Once you know where you are, you will naturally want to see what is around you, which leads us to the ls command. Listing the contents of a directory provides immediate feedback, but the raw output is often insufficient. By using flags, we gain deeper insight. For instance, the -L flag produces a long listing that displays permissions, owner information, and timestamps. Adding the -A flag ensures that you also see hidden files, which in Linux are identified by a leading dot in their name. If you are dealing with large directories, combining these with -H provides human-readable file sizes, such as megabytes or gigabytes, instead of raw block counts. The -R flag enables a recursive listing, showing the contents of subdirectories, effectively mapping out the tree structure beneath your feet. Moving through this structure requires the change directory command, or CD, which acts as your primary engine for navigation. You can use absolute paths to jump directly to any location from the file system root, or use relative paths to move based on your current position. For example, typing two dots, which represent the parent directory, allows you to move upward in the tree, while CD followed by a tilde brings you instantly to your user's home directory. While navigating, you should embrace the power of tab completion, a feature that significantly increases your efficiency and reduces typing errors. By pressing the tab key after typing only the first few characters of a file or directory name, the shell will automatically complete the string for you, or list the available possibilities if multiple matches exist. This is not just a convenience. It is a defensive programming habit that prevents mistakes when working with complex or deeply nested paths. Creating and organizing your workspace is handled by the mkdir and rmdr commands, which are essential for maintaining a clean file system hierarchy. The mkdir command creates a new directory, and when combined with the -p flag, it can construct entire parent-child directory trees in a single pass without throwing errors if the parent already exists. Conversely, rmdir is used to remove empty directories, acting as a safeguard to ensure you do not inadvertently delete files that might be contained within a folder. If you find your terminal window becoming cluttered, the clear command resets the display, allowing you to focus on your current objective without the distraction of previous output. Furthermore, keeping an eye on your command history is invaluable, as pressing the up arrow key allows you to recall and edit previously executed commands. This history is saved in a file within your home directory, allowing you to reuse complex strings without rewriting them from scratch each time. Mastering these basic primitives creates the foundation upon which all Linux system management rests, regardless of the distribution you eventually choose to specialize in. Consistent, deliberate practice in these navigation tasks will allow the mechanics to become second nature, freeing your mental bandwidth to focus on more complex administrative challenges. See you in the next lecture. Welcome back. In this chapter, we will explore the essential mechanics of file management and manipulation within the Linux environment. To effectively navigate a Linux system, you must master the fundamental tools for handling files and directories. The cp command allows you to duplicate files and directories, and when dealing with nested structures, the recursive flag is indispensable. By appending the -r option to your copy command, you instruct the shell to traverse subdirectories and preserve the entire tree structure. Moving files, which conveniently doubles as a renaming mechanism, is handled by the mv command. Unlike a simple copy, moving an item updates its location in the inode table without duplicating the data content. When you move files across different file systems, you might notice slightly slower performance as the system must physically copy and then delete the original entries. Mastery of these two utilities forms the bedrock of automation and daily system maintenance tasks. Data destruction is a task that carries significant risk when performed at the command line. The rm command provides the interface for removing files, but caution is necessary because there is no trash bin in the terminal. Using the -r flag enables recursive deletion, which is required for non-empty directories, while the -f flag forces the operation by suppressing prompts. You should be extremely careful with force recursive deletions, specifically when executing them as a root user, as you can easily erase critical system configuration files. Before running such commands, it is good practice to verify your current working directory using the pwd command. Understanding that these actions are permanent helps you cultivate a disciplined approach to your file system interactions. Maintenance often requires creating placeholders or updating timestamps on existing entries, which is where the touch command becomes relevant. When you run touch on a file that does not exist, the kernel creates an empty file with 0 bytes. If the target file already exists, touch simply updates both the access and modification timestamps to the current system time. This is particularly useful for scripting workflows where you need to trigger a specific event or signal that a task has recently been completed. Beyond simple creation, touch is a lightweight way to initialize a workspace without opening a text editor or invoking complex redirection operators. It serves as a simple yet powerful tool for keeping your directory state synchronized with your procedural logic. Efficiency in the terminal is often a matter of how well you can wield globbing patterns. By using the asterisk character, you can perform bulk operations on any number of files that share a common naming convention or extension. The question mark acts as a single character wildcard, allowing for more granular filtering when you need to match specific digits or letters in a sequence. These shell expansions are resolved before the command is even executed, meaning the tools like CP or RM receive a full list of expanded arguments. Mastering these patterns allows you to clean up directories or migrate batches of logs without manual intervention. It is a fundamental skill that demonstrates the difference between an amateur user and a power user. Understanding how the system references data requires a clear distinction between hard links and symbolic links. A hard link is essentially an additional directory entry pointing to the same data block or inode on the storage medium. Because hard links cannot span across different partitions, they are limited to the file system where the file resides. Conversely, a symbolic link is a special file that contains a path pointing to another file or directory elsewhere in the hierarchy. You create symbolic links using the "un" command with the "-s" flag, which provides flexibility by allowing pointers to traverse mount points and partitions. Symbolic links act like shortcuts, meaning that if you delete the original file, the link becomes broken and effectively useless. Look forward to our next discussion as we continue through the system. Welcome back. In this session, we will examine the standard tools and mechanisms Linux provides for displaying, navigating, and manipulating file content within the terminal environment. The cat command, short for concatenate, is perhaps the most fundamental utility for viewing file contents. When you pass a file name to cat, it reads the entire file and directs the text to standard output, which is typically your terminal screen. While this is efficient for small configuration files, it becomes impractical for larger files because the text scrolls past your view instantly. You might use cat to quickly inspect a short script or a list of shell environment variables. Because cat is designed to concatenate, you can also provide multiple file names to display them sequentially in a single output stream. This utility is a building block for more complex operations, particularly when combined with redirection or piping. When dealing with files that span thousands of lines, terminal buffers become overwhelmed, necessitating the use of pagers like less. Unlike cat, less allows you to navigate forward and backward through text files, which is essential for reading system logs or documentation. You move through the document using arrow keys, the spacebar to jump ahead by a page, or the B key to page backward. The less utility also provides powerful search capabilities, initiated by typing a / followed by your search term. To exit this interface, simply press the Q key to return to your bash prompt immediately. This tool is vastly preferred over More, which is an older, more limited pager that only supports forward navigation and remains largely for historical compatibility. Monitoring logs in real time requires different tools, as you are rarely interested in the entire file history when troubleshooting an active service. The tail command is the industry standard for this task, especially when employed with the -f flag. This flag instructs the utility to follow the file, meaning it will continually display new lines as they are appended to the log on the disk. For example, if you are observing a web server error log, tail allows you to spot issues as they occur without manually refreshing the output. Conversely, the head command is useful when you only need a quick preview of the file's inception, such as checking the first 10 lines to identify the structure of a CSV document or a data export. To truly master the Linux shell, one must understand the concept of standard streams: standard input, standard output, and standard error. Every process interacts with these three streams, where standard input represents data flowing into a program, while output and error represent data flowing out. Redirection operators allow you to manipulate these paths, such as using the greater than symbol to send standard output into a new file. If you use two greater than symbols, you append the output to an existing file instead of clobbering its current contents. Using the less than symbol, you can redirect the contents of a file to serve as the input for a command that would otherwise wait for keyboard entry. Pipes represent the most versatile mechanism for linking commands together by connecting the standard output of one process to the standard input of another. By utilizing the vertical bar character, you can create a chain of operations where each component performs a specialized task. A classic example is piping the output of cat into less to make large file content readable at your own pace without cluttering your shell history. You can even pipe output into text processing tools to filter results or calculate line counts before the data ever touches your physical disk. Mastering these conduits enables you to build ad hoc workflows, transforming simple command line tools into a powerful and cohesive administrative environment for your daily system operations. I will catch you in the next one. Welcome back. In this lecture, we will explore the mechanisms Linux uses to control access to files and directories by managing their ownership and permissions. At the core of Linux security is the concept that every object on the file system has an owner, a group, and a set of permission bits. When you run a command like lsl, you see a string of 10 characters, such as dwsxsr, x appearing at the far left of the terminal output. The first character denotes the file type. AD indicates a directory, while a hyphen indicates a regular file. Following this, the next 9 characters are grouped into 3 triplets representing read, write, and execute permissions for the owner, the group, and finally, all other users on the system. You can interpret these triplets as sequences where R stands for reading, W for writing, and X for executing, with a hyphen indicating that the specific permission is absent. For instance, RWX means the user can read the file, modify it, and execute it if it is a program. Understanding this notation is fundamental because it essentially acts as the gatekeeper for every interaction your shell has with the files on your disk. To modify these access levels, we primarily rely on the chmod command, which provides 2 distinct ways to define requirements. Symbolic mode uses letters such as U for user, G for group, O for others, and A for all, combined with operators like plus to add or minus to remove permissions. If you want to make a file executable by its owner, you simply run chmod u plus x file name. Conversely, numeric mode employs an octal system where read equals 4, write equals 2, and execute equals 1. You calculate the permission for each class by summing these numbers, resulting in a single digit from 0 to 7. For example, a numeric value of 755 translates to read, write, and execute for the owner, while group and others receive only read and execute writes. Mastering both notations is essential for the exam, as numeric mode offers precise control and a concise format, while symbolic mode is often more intuitive for single administrative changes. Beyond basic read and execute writes, Linux provides special permission bits known as the setuid, setgid, and sticky bits. The setuid bit allows a user to run an executable with the permissions of the file owner rather than their own, which is crucial for commands like passdoes that need to update the shadow file. When you set the setgid bit on a directory, any files created within that directory inherit the group ownership of the directory itself rather than the primary group of the user who created the file. The sticky bit, often seen on directories like TMP, ensures that only the file owner, the directory owner, or the root user can delete or rename files within that directory. These bits are represented by specific values in an octal position preceding the standard triple, and they are critical for maintaining security in multi-user environments. You will encounter these often when dealing with collaborative directories or system binaries that require elevated privileges to function correctly. Establishing the primary owner and group of a file is managed respectively by the chown and chgrp utilities. The command chown allows an administrator to change the owner of a file, and it can optionally update the group simultaneously by using a colon separator. For example, executing chown user group file name changes both the owner and the group in a single operation. The chgrp command is more specialized and only modifies the group ownership, following the same syntax and behavior as chown. It is important to remember that changing these attributes typically requires root privileges, because security policies generally prevent users from simply giving away their files to hide their activities. These ownership commands form the second layer of the permission model, ensuring that files are correctly associated with the appropriate users and groups for system organization. Finally, we arrive at the UMask, which serves as a mask to define the default permissions for any new file or directory created by a user session. Unlike permissions that explicitly grant access, the UMask subtracts bits from the default operating system settings to ensure a minimum security posture. If the default mode for a file is 666 and your UMask is 0222, the resulting permission for a new file will be 644, which inhibits others from writing to your data. Understanding how to calculate this subtraction in Octal is a common requirement for configuring secure environments where you want to prevent new files from being publicly writable. By setting a strict UMask in initialization files like bashrc, administrators ensure that security is not left to chance, but is instead enforced by default the moment a work object is created. Effectively balancing these defaults with explicit permission changes provides the depth required to secure a production Linux server against unauthorized access. I will see you in the next lecture. Welcome to the chapter on text manipulation in Linux, where we will master the essential command line tools for searching, parsing, and transforming data. By the end of this section, you will possess the ability to automate complex text processing tasks that are vital for any system administrator. This module is designed to provide you with the practical skills necessary to succeed in your professional career and pass the LFCA exam with confidence. You will learn to manipulate data streams using industry-standard utilities that every Linux expert relies on daily. We will start by examining the grep utility, an indispensable tool for pattern matching and text searching that utilizes regular expressions to pinpoint specific data within files. Next, we will explore the cut command, which allows you to extract specific columns from delimited files such as CSVs or system configuration files like /etc/passwd. The curriculum continues with an introduction to SED, known as the stream editor, which is a powerful mechanism for finding and replacing text strings on the fly without needing an interactive editor. Following that, we will dive into the aux command, a sophisticated field processor that serves as a mini programming language for generating reports and performing mathematical summations of data. To tie these concepts together, we will discuss how to implement pipes, which allow you to connect the output of one command directly into the input of another. This technique is frequently paired with sort, unique, and WC to efficiently count lines, words, and characters, enabling you to extract meaningful insights from raw system outputs. Improving your fluency in these text processing tools will significantly reduce your workload and increase your efficiency when managing Linux systems. I will see you in our first deep dive into the grep tool. Welcome back. In this lecture, we will explore the essential terminal-based text editors that you must master to effectively manage configuration files on a Linux system. Working in a terminal environment often requires editing configuration files directly on the server, where graphical user interfaces are typically absent. You might encounter several editors during your work, such as Nano, Emacs, or Vim. Nano is often praised for its simplicity and accessibility for beginners, as it displays basic command shortcuts at the bottom of the screen. Emacs is a highly extensible and powerful environment that goes well beyond simple text editing, though it often requires a steeper learning curve. However, for the purposes of the LFCA exam and general system administration, Vim remains the industry standard you will encounter on almost every distribution. Understanding how to operate within these environments without a mouse is a fundamental skill for any Linux professional. Vim operates using a modal paradigm, which distinguishes it from the standard word processors you might be accustomed to in a desktop environment. When you open a file in Vim, you start in command mode, where your keyboard input is interpreted as instructions for the editor rather than characters to be inserted into the document. If you want to type text, you must explicitly switch to insert mode by pressing the I key. Once you are finished with your changes, pressing the escape key returns you to command mode, ensuring that subsequent keystrokes are again treated as commands. This distinction is crucial because it allows for rapid navigation and manipulation of text without the need to constantly move your hands to a mouse. Mastering a few key movements and operations within Vim command mode will significantly increase your efficiency when editing system files. To delete a complete line, you simply press DD, which removes the current line and saves it into the buffer. If you wish to copy information, you can use YY to yank or copy the current line. Once you have copied or deleted a line, moving to your desired location and pressing P will paste the contents of your buffer after the cursor. These three operations, deleting, yanking, and pasting, form the backbone of most text manipulation tasks you will perform. Practicing these sequences in a sandbox environment will build the muscle memory required to perform these updates quickly and confidently. The final step in the editing cycle is ensuring your changes are correctly persisted to the disk before you exit the editor. While you are in command mode, you access the command line prompt within Vim by typing a colon, followed by specific instructions. Typing WQ and hitting enter tells Vim to write the changes to the file and subsequently quit the editor, returning you to your shell. If you happen to make mistakes and wish to abandon your changes, you can use Q to force quit without saving. This workflow is central to managing system configuration files where accuracy and the ability to roll back changes are vital for maintaining system stability. Mastering the transition between these modes ensures you can navigate the terminal with precision and handle any configuration task you face. See you in the next lecture. Welcome back. In this chapter, we will explore the essential utilities for locating files and system binaries to navigate the vast Linux file system efficiently. When working within a Linux environment, one of the most fundamental skills is the ability to track down files based on specific attributes. The find command is arguably the most powerful tool for this purpose because of its ability to traverse the directory tree in real time. By utilizing parameters such as name for file identifiers, size for storage footprint, and type to distinguish between regular files and directories, you maintain precise control over your searches. You might, for example, search for all configuration files larger than 10 megabytes that were modified in the last week using the nametime flag. Because find iterates through live directory structures, it is incredibly accurate, though it can consume significant I/O resources on large file systems. Mastering this command allows you to locate critical data even when you have only partial information about its origin. In contrast to the real-time nature of find, the locate command provides a much faster, albeit slightly different, experience. It relies on a pre-built database, typically managed by a background process known as updated DB, which indexes the file system periodically. When you run a search, you are querying this index rather than performing a live walk of the directories, making results return almost instantaneously. However, because the information depends on the frequency of the database update, the results can occasionally be stale if a file was created or moved immediately before your query. You can manually trigger an update to ensure accuracy, though this requires administrative privileges and will cause the system to spike in resource usage while scanning the disks. Understanding this trade-off between speed and data freshness is essential for choosing the right tool for your specific investigation. Beyond general file searching, you will often need to identify the exact location of software binaries that you intend to execute. This is where the which and whereis commands become indispensable in your daily workflow. The which utility searches the directories defined in your path environment variable to return the absolute path name of the first executable it finds that matches the command name. Conversely, whereas offers a broader scope by locating source, binary, and manual page files associated with a program across standard binary directories. If you have ever wondered why a specific version of a tool is running instead of another, these utilities provide the visibility required to diagnose configuration issues. They rely on the system hierarchy, which dictates that binaries typically reside in bin, /bin, or /local/bin, ensuring that your system remains organized and predictable. Finally, we must address the grep utility, which is primarily known for searching the textual content contained within files. While the previous tools focus on metadata such as file names and locations, grep allows you to search for patterns or specific strings of text within a directory structure recursively. By using the R flag, you can force the utility to scan through every file in a directory and its subdirectories, effectively turning your terminal into a powerful text indexing machine. This is particularly useful for system administrators who need to find specific configuration errors or log entries across multiple service files simultaneously. When combined with other commands through piping, it becomes a versatile filter, allowing you to narrow down mountains of output into actionable information. Developing the habit of using these tools in tandem will transform your interaction with the Linux file system from a tedious search into an automated precision task. See you in the next lesson. Welcome back. In this chapter, we are going to explore the mechanics behind software package management and how these systems handle the life cycle of applications within a Linux distribution. Software package management is fundamentally about transforming raw source code into consumable, installable units that the operating system can track and maintain. When you install an application, you are not simply copying files into a folder. You are registering metadata, dependencies, and configuration templates with a centralized database. This database acts as a single point of truth for what is currently residing on your disk. Without this abstraction, the manual effort required to track shared libraries and binary files would quickly become unsustainable for any complex system. Most modern Linux distributions rely on a hierarchical structure where high-level package managers query remote repositories to satisfy the complex tree of dependencies that software requires to function correctly. On Debian-based systems like Ubuntu, the Advanced Package Tool, commonly known as APT, serves as the primary interface for users to fetch and resolve dependencies. Beneath this high-level layer sits dpkg, which is the low-level utility responsible for the actual unpacking and configuration of individual deb files. If you run an update, APT synchronizes your local cache with the remote repository index to determine which packages have newer versions available. When you perform an installation, the system checks whether the required libraries exist. If not, it automatically pulls down any supplementary packages needed to ensure the software runs without errors. This automated resolution process is a significant evolution from the early days of Linux, where users frequently encountered the infamous dependency hell. Conversely, Red Hat-derived systems utilize the RPM package manager as their low-level engine, while DNF, or its predecessor Yum, handles the high-level logic. While the fundamental concepts remain the same, the command syntax and the internal package formats differ significantly from their Debian counterparts. DNF maintains its own metadata about installed software, tracking which repository provided a package and verifying it against digital signatures to ensure integrity. The ability to manage these repositories is critical, as it dictates where your system looks for updates and security patches. By adding third-party repositories or personal package archives, you extend the system's reach beyond the baseline offerings provided by the distribution vendor. However, adding third-party sources introduces a shift in the security model that you must handle with care. Every package you download should be accompanied by a cryptographic signature that verifies the provenance of the software and ensures that the binary has not been tampered with during transit. If you add an untrusted repository, you lose the assurance that the code originates from a reputable source, which increases the surface area for potential supply chain vulnerabilities. Always rely on official repository keys to authenticate software, as these keys act as a gatekeeper for your system's trust store. Understanding how to manage these keys and the repositories they govern is a core skill for any professional maintaining a production Linux environment. Maintenance involves more than just installation. It also concerns the software update cycle and the removal of unused binaries. Over time, cache data can consume significant disk space, making it necessary to periodically purge old packages and clear local repository indices. Removing software requires a clean approach where both the application and its unnecessary dependencies are stripped away, preventing system bloat. Monitoring these packages ensures that you maintain a lean and predictable environment, which is the hallmark of effective system administration. By mastering both graphical and command line interfaces for these tasks, you develop the versatility required to manage Linux systems regardless of specific distribution flavors. I will see you in the next lesson. Welcome back. Today, we are diving into the architecture of user and group management, ensuring you have the skills to maintain system security and identity integrity. At the heart of Linux identity management lies a specific set of text files that store user and group information. The most important of these is s/etc passwd, which contains records for every user account, including their username, UID, GID, home directory path, and default login shell. You will notice that while this file is world readable, the actual password hashes are stripped out and stored in /etc/shadow. This separation of concerns is a fundamental security precaution, as it ensures that sensitive authentication data remains accessible only to privileged accounts. Similarly, group definitions reside in the etc. group file, which maps group names to their respective GIDs and a list of secondary members. Understanding the structure of these plain text files is essential because, while utilities exist to modify them, a system administrator often needs to inspect them directly to troubleshoot configuration issues or account conflicts. Beyond manual inspection, we rely on standard commands to manage accounts without risking the syntax errors that manual editing might introduce. When you need to create a new user, userad is your primary tool. It creates the necessary entry in/etc passwd and can automatically generate a home directory and copy default shell configuration files. The usermod command is then used to modify existing attributes, such as changing a user's primary group, modifying their comment field, or locking an account when an employee leaves the organization. When an account is no longer needed, the userdel command allows for the safe removal of user identity information. It is important to note that without the appropriate flags, these commands might leave orphaned files behind in the file system. So always consider whether you need to perform a cleanup of the user's home directory during the deletion process. Managing groups requires a slightly different approach, as groups act as organizational units for resource access control. The group_add command is used to define new groups, while adding users to those groups is typically handled with usermod using the secondary group association flags. When you assign a user to a group, you control their ability to access files or services that aren't globally readable or executable. This is the cornerstone of the principle of least privilege, as it restricts a user's scope to only what is necessary for their job function. By grouping users intelligently, you reduce the complexity of individual file permission assignments, which in turn simplifies your overall security posture and makes auditing access much easier as the system scales. Password management and security policies are enforced through utilities like passwd and change to ensure compliance with organization-wide standards. While passwd handles the initial setup or change of a user's authentication token, change is much more powerful for policy enforcement. Using change, you can mandate password expiration, set a minimum number of days between password changes, or define a warning period before a password expires. This allows you to enforce regular password rotations, which remains a key mechanism for mitigating the risk of credential leakage. These settings are stored within the e/etc/shadow file, acting as a direct control mechanism for the authentication subsystem. Monitoring these settings through the command line provides immediate feedback on whether your user base is maintaining acceptable security hygiene. Granting administrative privileges necessitates a disciplined approach, and this is where the sudoers file and the visudo command come into play. Never attempt to edit the /etc/sudoers file with a standard text editor, as a single syntax error can render administrative access impossible, effectively locking you out of your own system. The visudo command acts as a wrapper that performs a mandatory syntax check after you save your changes before committing the file to the system. This provides a safety net that prevents catastrophic misconfigurations. By defining specific privileges within the sudoers file, you grant users the ability to run restricted commands with elevated authority while maintaining an audit trail of who performed which administrative action. This practice is significantly safer than granting root access directly or sharing the root account's credentials across multiple users. See you in the next lesson. Welcome to this exploration of the Linux boot process and the systemd initialization framework. We will examine how a system transitions from power on to a fully operational state. When you press the power button on a modern computer, the process begins with the hardware firmware, specifically the Basic Input-Output System, BIOS, or the Unified Extensible Firmware Interface, UEFI. This firmware is responsible for a self-test of the hardware components and eventually locates a bootable device. It hands execution control over to the bootloader, most commonly grub2 in the Linux ecosystem. The bootloader then loads the Linux kernel into memory, along with an initial RAM disk, which provides the necessary drivers to mount the actual root file system. Once the kernel takes control, it initializes the system hardware and starts the first user space process, which historically was the init process, but is now almost universally systemed. The shift from the legacy sysvinit to systemed represented a fundamental change in how Linux manages service startup, dependency resolution, and parallel execution. Sysvinit operated using shell scripts executed in a strict chronological order based on run levels, which often led to slow boot times due to serial processing. Systemd, conversely, utilizes a mechanism of unit files to manage processes, or daemons, allowing for aggressive parallelization. A unit file defines exactly what a service is, how to start it, and crucially, what other services it requires to function correctly. By resolving these dependencies dynamically, Systemd ensures that services start as soon as their requirements are met, rather than waiting for a rigid sequence to complete. This transition has provided administrators with a more robust and predictable method for controlling the life cycle of background tasks on their systems. Managing services within a system-based environment revolves around the systemctl utility, which acts as the primary interface for the init system. To verify the state of a specific daemon, you perform a status query, which reports whether the process is active, inactive, or failed, while also providing a snippet of recent logs. If a service malfunctions, you can attempt to correct the issue using the restart command, or simply initiate a stop and start sequence to refresh the process. For services that are not required for specific workflows, administrators often use the disable command to ensure the daemon does not launch automatically during the next boot phase. It is important to note that these commands interact directly with the unit file stored on the disk, making the management of critical system components remarkably consistent across different Linux distributions. Beyond managing individual services, Systemd uses the concept of target units to define the overall state of the operating system after initialization. A target acts similarly to the old run levels, grouping together a set of services required for a specific operational mode. The multi-user target is typically used for server environments that do not require a graphical interface, focusing instead on networking and essential background processes. Conversely, the graphical target includes all the dependencies of the multi-user target while adding the services necessary for a display manager and a desktop environment. You can switch between these states dynamically using systemctl isolate, which shuts down unneeded services and brings up those required by the desired target. Understanding these targets is essential for configuring systems that need to maintain a specific footprint, particularly in constrained cloud or virtual environments. Troubleshooting the system initialization phase requires a deep understanding of the logging mechanisms provided by the journaled service. Since this service collects data from the kernel, boot processes, and user space applications, it serves as the authoritative source of truth for postmortem analysis. The journalctl utility is the primary tool used to query these binary logs, offering powerful filtering options based on time, process priority, or specific unit names. If a service fails to start during boot, you can examine logs from previous sessions to identify the specific exit code or dependency error that prevented the process from reaching an active state. Furthermore, Systemd provides built-in tools like Systemd Analyze, which outputs timing statistics for the boot process, allowing administrators to pinpoint which specific services are introducing latency. By analyzing these performance metrics and error reports, you can systematically optimize the initialization sequence and restore failed services to full operational capacity. See you in the next lecture. Welcome back, and today we turn our attention to the mechanics of controlling active processes within a Linux system. In this chapter, we will examine how the kernel orchestrates execution and how administrators intervene when resources become constrained. At the heart of Linux process management is the concept of the process ID or PID, which serves as a unique identifier for every running task. When a program executes, the kernel assigns it a PID, allowing the operating system to track its state, resource utilization, and ownership. Monitoring these processes is a fundamental skill, and this command remains the primary tool for this visibility. By running psaux, you gain a snapshot of every process currently executing, regardless of the user who initiated it or the terminal it is attached to. The utility of this command lies in its breadth, as it reveals the terminal status, start time, and the specific CPU and memory percentage consumed by each process. When you need a dynamic, updating view of these metrics, utilities like top or H2Top transition from static logs to interactive dashboards. These tools allow you to sort processes by resource usage, which is invaluable when identifying a runaway process that may be exhausting your available compute power. Once you've identified a process that needs attention, you must communicate with it, typically through signals. Signaling is the mechanism by which the kernel informs a process about a change in state or a request to cease execution. The kill command, despite its alarming name, is essentially a utility for sending these signals. A command like kill, sitterm, or simply kill, followed by a PID, sends a polite termination signal, allowing the process to close files and release memory before shutting down. If a process stops responding, you may need to escalate to sigkill, which forces the process to close immediately without allowing for a graceful exit. For those who prefer to address processes by name rather than hunting for a PID, the pkill command offers a streamlined alternative. Another critical signal is cgup, which is often used to instruct a daemon to reload its configuration files without a full restart. Mastering these signals provides the administrative control necessary to maintain uptime and recover from application stalls. Managing the flow of execution extends to controlling whether a job runs in the foreground or the background. When you start a command in the terminal, it occupies the foreground, meaning the shell waits for the process to complete before returning control to the user. Appending an ampersand to your command forces the process to run in the background, allowing you to continue using your shell immediately. If you have already started a process in the foreground, you can suspend it using Ctrl-Z and then use the BG command to resume it in the background. Should you later decide that the job requires interaction, the FG command moves it back into the foreground. This task switching is particularly useful when performing long-running file operations or network backups that you do not want to block your current work session. By manipulating these job states, you keep your terminal productive and your commands running efficiently in the background. Finally, we must consider the broader health of the system by analyzing load averages and total resource utilization. The three numbers displayed by top represent the average system load over the last 1, 5, and 15 minutes, respectively. As a rule of thumb, a load average that consistently exceeds the number of available CPU cores suggests that your system is struggling to keep up with the queue of pending tasks. Beyond CPU metrics, you should keep a watchful eye on memory consumption, as excessive swapping to disk can degrade system performance to the point of unresponsiveness. Consistently monitoring both CPU and RAM utilization allows you to spot patterns of resource exhaustion before they cause a hard outage. By understanding how to interpret these indicators, you gain the diagnostic capability to perform capacity planning and troubleshoot performance bottlenecks effectively. This proactive approach to process management ensures that the resources allocated to your applications are utilized with precision. I will see you in the next lecture. Welcome to the Storage and File Systems chapter, where we will demystify how Linux organizes, manages, and structures data on physical hardware. By the end of this module, you will have the technical proficiency required to handle enterprise-grade storage configurations with total confidence. Managing storage starts with identifying your physical devices and how they are partitioned. When you execute the lsbl key command, the kernel provides a tree-like view of all block devices, which is significantly more readable than scanning raw device nodes in the dev directory. If you need to verify disk space utilization or see how much room is left on a mounted volume, the df command with the H flag offers a human-readable summary of occupied and available blocks. For more granular control, such as creating or modifying partitions, fdisk serves as the standard tool for interacting with disk partition tables. Understanding these tools is fundamental because every operating system task, from log rotation to database management, implicitly relies on the integrity of the underlying storage layer. You are not just managing bits on a platter or a flash cell, you are managing the availability of the entire environment. Linux supports a rich ecosystem of file systems, each designed with specific trade-offs regarding reliability, performance, and features. The extension 4 file system remains the workhorse for most general-purpose distributions due to its stability and long-term support. In contrast, XFS is often favored for large-scale enterprise storage because of its superior scalability and parallel I/O processing capabilities. BTFS represents a more modern approach, focusing on advanced features like snapshots, copy-on-write functionality, and integrated volume management, which simplifies data protection. Choosing the correct file system is a matter of matching your architectural requirements to the specific design philosophy behind the implementation. You must understand these variations because the file system type determines how the kernel manages enode tables, metadata journaling, and the overall robustness against power failures. Once a partition is formatted with a file system, it must be integrated into the global directory hierarchy through a process known as mounting. The mount command performs this action by linking a device node, such as dev/sda1, to a specific directory path called a mount point. However, manual mounting is ephemeral and will disappear after a system reboot, which is where the fstab file becomes critical. By adding an entry to the etc. or fstab file, you instruct the system to automatically attach these storage resources during the boot process based on defined parameters and file system identifiers. This configuration requires careful attention to detail, as an incorrect entry can lead to boot failures or the system dropping into an emergency maintenance shell. It is the bridge between temporary attachment and permanent system infrastructure. Logical Volume Management, or LVM, provides an abstraction layer that allows you to treat storage as a pool of resources rather than fixed physical constraints. This architecture starts with physical volumes, which are the raw partitions assigned to the LVM subsystem. These physical volumes are aggregated into a volume group, effectively creating a storage reservoir that can be expanded or shrunk as needed. Within this volume group, you define logical volumes, which behave like standard partitions but carry the distinct advantage of being resizable without unmounting the file system. LVM is essential for modern server environments because it allows administrators to grow storage dynamically without downtime, providing the flexibility required by modern applications. It represents a shift from static hardware management to flexible software-defined storage allocation. Monitoring your disk utilization is a preventative measure every administrator must perform to ensure system health and continuity. When a file system reaches full capacity, critical processes that depend on writing temporary files, logs, or state data will inevitably fail, potentially leading to cascading system crashes. You should regularly audit your mounts using the df command to identify partitions trending toward full utilization before they hit the critical threshold. It is also common practice to isolate data directories like var or home onto separate partitions to ensure that a runaway process filling up space does not stall the entire operating system. By maintaining awareness of your storage footprint, you proactively defend the stability of the services running atop your Linux environment. The discipline of storage planning is often the difference between a resilient system and one that requires constant firefighter-style intervention. I will see you in the next lecture. Welcome back to our journey through the Linux operating system, where we now turn our attention to the critical task of system logging and auditing. This chapter will equip you with the essential skills to monitor system health and ensure security through the diligent observation of log files. In any production environment, logs serve as the primary source of truth for understanding how a system behaves under load or when things go wrong. Without a structured approach to logging, an administrator is essentially flying blind, unable to correlate specific user actions with system instability or security breaches. The Linux directory located @var/log acts as the central repository for most of these artifacts, containing everything from authentication attempts to kernel messages. When you navigate this directory, you will encounter files like auth.log, which tracks login attempts, and syslog, which captures a broad spectrum of general system events. Furthermore, the dimsg command outputs the message buffer from the kernel, providing immediate insight into hardware initialization and driver-related issues. By mastering these locations and commands, you place yourself in a position to diagnose problems long before they manifest as critical service failures. While manual inspection of flat files in /var/log is foundational, modern Linux distributions leverage the systemed ecosystem to provide more sophisticated management through journal TDL. Unlike static text files, the journal stores logs in a binary format, which allows for extremely efficient searching and filtering capabilities. You can invoke journalctl with specific flags to isolate logs by a particular unit, such as a web server process, or filter by a precise time frame to narrow down when an event occurred. This utility also allows you to query logs based on priority levels, ranging from debug information to critical emergency alerts, which significantly reduces mental fatigue when parsing large volumes of data. Understanding how to pipe these commands or use built-in parameters is a non-negotiable skill for anyone aiming to clear the LFCA certification. It transforms the act of troubleshooting from a tedious grep operation into a surgical extraction of relevant events. As system activity grows, so does the volume of generated log data, which introduces the risk of exhausting available disk space and potentially crashing the system. This is where the logrotate utility becomes indispensable by automating the archiving and truncation of log files according to a defined schedule or size threshold. A typical configuration file for logrotate dictates how many old copies should be kept, whether files should be compressed to save space, and what actions to perform after rotation, such as notifying services to start new log files. By offloading this task to the system, you ensure that you maintain historical safety for incident response without the manual overhead of constant monitoring. Furthermore, in larger infrastructures, you might consider configuring RSSlog to ship these logs to a centralized server. Centralization is vital because it prevents an attacker from tampering with local logs to hide their tracks after gaining unauthorized access to a single host. When we look at auditing and logging, we must recognize that this process is twofold. It is simultaneously a reactive practice for debugging and a proactive requirement for security compliance. If a system experiences a kernel panic or an unauthorized user attempts to escalate their privileges, the system log will almost certainly contain the breadcrumbs needed for a post-mortem analysis. Relying solely on real-time monitoring is insufficient because it does not account for the historical context provided by rotated files. Consequently, your ability to configure rotational policies that balance storage constraints with the need for long-term retention is a hallmark of a mature administrator. Effective logging enables an environment of transparency, where every significant transition in the system state is recorded and accessible for audit. I look forward to seeing you in the next session. Welcome back. In this chapter, we will explore the essential tools for automating system tasks, specifically focusing on how to schedule recurring jobs and execute one-time commands to maintain a Linux system. Automation is the cornerstone of efficient system administration. Instead of manually running cleanup scripts or backups, you should rely on the operating system to perform these operations at predefined intervals. By mastering job scheduling, you reduce the risk of human error and ensure that critical background tasks occur reliably without your constant intervention. We will cover the specific tools built into the Linux kernel and user space designed for this purpose, providing you with the practical skills required to automate your workflow effectively. The most prominent tool for recurring tasks is the cron daemon, which checks the system for scheduled jobs periodically. Each user on a Linux system can maintain their own cron tab file, a configuration file that dictates which commands to run and when. The syntax of a cron tab entry is highly specific, consisting of 5 time fields followed by the absolute path to the command or script you wish to execute. The fields represent the minute, hour, day of the month, and day of the week, in that order. For example, a setting of 0 for the minute and 2 for the hour will trigger a job at 2 a.m. every single day. Using asterisks in these fields acts as a wildcard, indicating that the task should run for every possible value in that increment. Beyond simple time increments, the cron tab syntax allows for list manipulation using commas or ranges using hyphens. If you want a task to run every Monday and Friday, you can specify that in the day of the week field, where Sunday is represented by 0 or 7. Advanced users often utilize special shorthand strings such as @daily or @reboot, which simplifies complex timing requirements into human-readable labels. It is vital to remember that tasks run with the privileges of the user who owns the cron tab file, which is a crucial consideration for security. If a script requires elevated permissions to perform a system-wide backup, it must be placed within a root-owned cron tab or the relevant system-wide directory. While users manage their personal schedules through individual cron tabs, system-wide automation typically resides in the SS/directory structure. You will frequently interact with etc/cron tab and the r/cron.d/directory, where system packages drop their own scheduled tasks. Unlike user cron tabs, these files include an additional field to specify which user account should run the command. Placing a configuration file inside etc/cron.d is the preferred method for sysadmins to manage automated updates or log rotation scripts because it keeps the configuration modular and distinct from the global system cron tab. Always ensure that these scripts have the correct execute permissions and that they use absolute paths to invoke binaries, as the environment variables in a cron session differ significantly from your interactive shell. Sometimes the requirement is not to run a task on a recurring basis, but rather to perform a one-time operation at a specific time in the future. For this, we turn to the at command, which provides a queue-based system for delayed execution. When you run it followed by a time, such as noon or 5 p.m., the utility opens an interactive prompt where you can type the commands you wish to execute. Pressing Ctrl-D signals the completion of your command block, and the job is added to the system queue. You can list pending jobs using ATQ and remove them by their job number using the atrum command, providing a flexible way to handle tasks that do not fit into the standard cycle of a cron job. When writing scripts for automation, it is best practice to redirect output to a log file to ensure you have a record of success or failure. Since cron jobs do not typically display output to a terminal, any error messages generated during execution might otherwise be lost. Appending both standard output and standard error to a file, using the common redirection syntax, allows you to audit your automated backups or clearance scripts efficiently. Without this, your automation might fail silently, leaving your system in an inconsistent state while you believe the tasks are proceeding correctly. As you gain more experience, you will learn to construct robust scripts that check for the existence of files or sufficient disk space before attempting to perform operations. See you in the next lecture. Welcome to this chapter on understanding system hardware, where we will demystify how Linux interacts with the physical layer of your computer. You will master the tools required to interrogate your machine's internals and troubleshoot complex hardware issues with confidence. When we interact with a modern Linux system, we are often shielded from the underlying hardware by layers of abstraction. But as administrators, we must eventually pierce that veil. The kernel serves as the fundamental bridge between the software we run and the physical transistors and circuits that perform the work. To inspect the processor topology of your machine, you will frequently turn to the LSCSPU command. This utility provides a succinct summary of your CPU architecture, including the number of physical cores, threads, and even cache sizes. If you need a more granular, comprehensive hardware inventory, the LSW utility is your primary diagnostic tool. By invoking LSW, often elevated with administrative privileges, you generate a detailed tree of the entire system structure. This includes information on memory banks, firmware versions, and storage controllers, which provides the necessary context when you are planning hardware upgrades or investigating performance bottlenecks. Beyond the integrated components, we must also account for peripherals connected through various bus architectures, most notably the Universal Serial Bus. The LSESB command is standard for identifying these connected devices, listing vendor and product IDs that are essential for matching hardware with the correct driver software. However, knowing what is plugged in is only half the battle, as we must also understand how the kernel communicates with these devices through interrupts and I/O ports. Interrupts are signals sent to the processor to indicate that an event requires immediate attention, such as a keystroke or a data packet arrival. You can monitor these communications by examining the flashproc/interrupts file, where the kernel keeps a live registry of how IRQs are distributed across your hardware. Analyzing these assignments helps you identify resource contention where multiple devices might be vying for the same request line, which once was a major concern but remains useful knowledge for understanding system throughput. The Linux kernel is a modular beast, meaning it does not carry every possible device driver in its base memory footprint. Instead, it utilizes loadable kernel modules to add functionality on demand, which keeps the kernel efficient and stable. You can verify your current kernel version and system architecture by running the uname command with the appropriate flags, typically unamr for the release information. To see which modules are currently active and loaded into memory, you will use the lsmod command. When you need to load a specific driver or remove one that is malfunctioning, the modprobe command is the standard interface. Unlike older utilities that required manual dependency resolution, modprobe intelligently handles the loading of underlying requirements, preventing the common pitfalls of driver mismatching. This system of modules is why your hardware is automatically recognized as you plug it in, provided the necessary kernel object file exists in the file system. Even with the most robust modules, hardware will occasionally behave in ways that defy expectations, leading to performance degradation or total failure. The primary mechanism for diagnosing these issues is the kernel ring buffer, which serves as a chronological record of system events starting from the boot process. By using the dimsg command, you can tail these messages to look for hardware-specific errors, such as thermal throttling reports or disk I/O errors that suggest imminent failure. It is often useful to pipe the output of dimsg through a text filter like grep to isolate relevant strings, such as disk identifiers or interface names. This capability allows you to confirm whether or not a specific peripheral is correctly initialized by the kernel drivers. By mastering these diagnostic commands, you transform from a casual user into a capable administrator who views the machine as a cohesive, integrated system rather than a black box. I look forward to our next session together. Hello. In this section, we examine the fundamental delivery models of cloud computing to understand how modern infrastructure supports scalable applications. Cloud computing is fundamentally about abstracting hardware and software layers to provide services over the internet, rather than relying on local physical servers. At the lowest level of abstraction, we have infrastructure as a service, or IaaS, which provides raw compute, storage, and networking capabilities. When you interact with tools like AWS EC2, Google Compute Engine, or Microsoft Azure Virtual Machines, you are essentially renting virtualized hardware. This model shifts the responsibility of physical security, power, and cooling to the host, while you remain responsible for the operating system, middleware, and application runtime. It is a highly flexible approach that mimics traditional data center operations, but offloads the most cumbersome physical maintenance tasks to a provider. The primary benefit is the granular control it grants over the stack, allowing you to configure virtual networks and storage volumes just as you would in an on-premises environment. Moving up the ladder of abstraction, we encounter Platform as a Service, or PaaS, which focuses more on the development lifecycle than the underlying infrastructure. With PaaS, you no longer manage the operating system, security patches, or runtime updates, as these are handled by the cloud provider. Instead, developers focus exclusively on their application code and data configurations. Examples include Google App Engine, Azure App Service, and AWS Elastic Beanstalk, which abstract the server layer entirely. This allows for faster deployment cycles because the provider ensures the environment is scaled and optimized for the specific frameworks you are using. It is an ideal middle ground for teams that need to deploy quickly without the administrative overhead associated with managing operating system kernels or persistent security patching routines. At the highest level of abstraction, we find software as a service, or SaaS, which is the model most people encounter in their daily professional or personal lives. In a SaaS delivery model, the provider manages the entire stack, from the physical infrastructure and operating system down to the final user interface of the application. End users simply access these services through a web browser or API, without ever needing to know what happens in the backend. Common examples are Google Workspace, Microsoft 365, and various customer relationship management systems where you simply pay for access to a functional tool. Because the provider maintains full control over the application, the responsibility for updates, security, and uptime rests almost entirely with them. This removes nearly all technical management burdens from the user, making it the most accessible but least customizable cloud service model. Understanding these models is incomplete without grasping the shared responsibility model, which dictates where the provider's obligations end and yours begin. Irrespective of the model, you are always responsible for your own data and access management, even if the provider furnishes the tools to protect them. In IaaS, you own everything from the operating system upward, while in SaaS, Your responsibility is limited mostly to identity and access configuration. This model acts as a contract of sorts, ensuring that security gaps are not created by misunderstandings about who handles the firewall configuration versus the application logic. Misalignment in this area often leads to misconfigured storage buckets or open ports, which is the most common reason for cloud breaches. Recognizing that the cloud is not essentially someone else's computer, but a contractually defined partnership is vital for any systems administrator. Clouds are also defined by specific traits such as on-demand self-service, broad network access, and measured resource usage. On-demand capabilities allow users to provision compute or storage resources automatically without human interaction with the provider. Broad network access ensures these services are available over standard protocols through diverse client platforms like mobile devices or workstations. Measured service implies that the system automatically controls and optimizes resource use by leveraging a metering capability appropriate to the type of service. These characteristics allow organizations to treat IT resources as utilities, much like the electricity or water grid that powers our homes and businesses. This elasticity is what allows a startup to scale to meet global demand without having to purchase hardware in advance, which is a massive shift from traditional capital expenditure models. Deployment strategies add another layer of complexity by defining the physical and logical boundaries of the infrastructure. A public cloud involves services offered to the general public or industry groups over the infrastructure owned by a provider like AWS or Azure. In contrast, a private cloud is infrastructure operated solely for a single organization, providing greater control and potentially better compliance with strict data sovereignty requirements. A hybrid cloud combines these two, allowing data and applications to move between public and private environments, which provides the best balance of security and flexibility. Choosing between these depends on your organizational risk appetite, budget, and performance needs. Most modern enterprises eventually landing on a hybrid approach to maintain some legacy control while reaping the innovation benefits of public cloud hyperscalers. See you in the next lecture. Welcome to this chapter where we will explore the core concepts of virtualization and how it enables modern cloud infrastructure. By the end of this module, you will understand the mechanics of hypervisors and how to optimize resource allocation for efficient system management. Virtualization is fundamentally an abstraction layer that decouples the physical hardware from the operating system, allowing multiple instances to share a single host machine. At its core, this technology uses a piece of software or firmware known as a hypervisor, which provides the environment for virtual machines to execute their own independent kernels. By intercepting calls from the guest operating system to the physical hardware, the hypervisor ensures that resources like CPU cycles, memory, and storage are distributed according to predefined configurations. This isolation is critical because it creates a sandbox environment for every virtual machine, preventing one instance from accessing the memory space or data of another. When you run a virtualized workload, the underlying physical processor perceives these guest operations as standard processes, yet the hypervisor manages the hardware scheduling to maintain performance and stability. This level of abstraction is what permits us to run disparate operating systems, such as a legacy version of a Linux distribution alongside a modern application server, on the same iron without conflict. We gain the ability to snapshot state, replicate environments, and move workloads across different physical servers with minimal downtime. To categorize these technologies, we distinguish between Type 1 and Type 2 hypervisors based on how they interact with the physical hardware. A Type 1 hypervisor, often called a bare metal hypervisor, runs directly on the host's hardware without the need for a host operating system. Examples include KVM, which is integrated into the Linux kernel, and VMware ESXi, which is designed explicitly for enterprise-grade data centers. Because there is no underlying general-purpose operating system to manage, Type 1 hypervisors are remarkably efficient, boasting high performance and lower overhead. In contrast, a Type 2 hypervisor, or hosted hypervisor, runs as an application on top of an existing, conventional operating system like Windows or a standard Linux desktop distribution. A popular example is Oracle VirtualBox, which serves as a great tool for personal learning or basic testing environments. While Type 2 hypervisors are easier to install and manage for day-to-day tasks, they suffer from higher latency because any instruction from the virtual machine must pass through the host operating system before touching the hardware. Effective virtualization requires a disciplined approach to resource allocation, specifically concerning the virtual CPU, memory, and storage subsystems. The hypervisor creates virtualized versions of these physical components, but it is important to remember that the total physical capacity of the host dictates the hard limit for all concurrently running virtual machines. Over-provisioning vCPU or memory can lead to significant performance degradation, as the hypervisor must constantly swap resource access between competing guests. Storage is usually handled via virtual disk images, which are essentially large files on the host file system that expand or shrink based on usage. By consolidating multiple traditionally separate server functions onto one physical host, we drastically reduce space requirements, power consumption, and thermal output in data centers. This paradigm shift towards consolidation is a cornerstone of modern cost reduction strategies, as it allows organizations to increase the density of their workloads rather than purchasing more physical hardware. Efficiently managing these resources means constantly monitoring the balance between utilization and total available capacity to ensure that no single guest starves another of the necessary cycles. See you in the next session. Welcome back. Let's explore the architectural distinctions between virtual machines and containers to understand their respective roles in modern infrastructure. When we talk about virtual machines, we are essentially talking about the emulation of a complete physical computer. Each virtual machine runs its own full guest operating system, which includes the kernel, system libraries, and the binary files required to boot. This approach relies on a hypervisor, a software layer that abstracts the physical hardware and partitions it into multiple isolated environments. Because the guest operating system is entirely independent of the host, you gain a high degree of security and isolation. However, this comes at the cost of significant resource overhead, as each virtual machine must dedicate a portion of the host's memory, CPU, and storage just to run its kernel. Boot times for virtual machines are also relatively slow, mirroring the behavior of a physical server that must execute a full cold start boot sequence before any applications can execute. Containers represent a fundamentally different paradigm where the isolation happens at the process level rather than the hardware level. Instead of running a full guest operating system, containers share the kernel of the underlying host machine. They utilize features like namespaces to isolate processes, network stacks, and file systems, and control groups to govern resource usage. Because there is no need to boot a full kernel, containers are incredibly lightweight and can start up in a fraction of a second. This efficiency makes them an ideal choice for microservices architectures, where you might want to spin up dozens or hundreds of small, single-purpose services rapidly. The reduced footprint allows for a much higher density of services on a single physical host compared to what is possible with traditional virtual machines. Portability is perhaps one of the most compelling reasons to choose containerization over virtual machine architectures. A container image encapsulates the application alongside all of its dependencies, configurations, and libraries, ensuring that it behaves identically across different environments. Whether you are running the image on a developer's local laptop, a staging server, or a production cluster in the cloud, the execution environment remains consistent. Tools like Docker provide a standardized format for building and shipping these images, which simplifies the pipeline from development to deployment. This eliminates the "it works on my machine" syndrome that historically plagues software releases. It is important to note that while containers offer excellent portability, they do not provide the same level of security isolation as virtual machines, since they share the host kernel. When determining the appropriate technology for your specific use case, you should consider the trade-offs between isolation and performance. Virtual machines are the industry standard when you need to run legacy applications that require a specific kernel version, or when strict security boundaries are the highest priority. If you're dealing with multi-tenant environments where total isolation between workloads is a legal or requirement hurdle, the virtual machine remains the safest bet. Conversely, container runtimes are designed for modern cloud-native applications that favor scalability and rapid deployments. If your goal is to optimize hardware utilization and streamline the transition between different infrastructure providers, the lightweight nature of containers will yield much higher operational efficiency. Understanding when to use one over the other is an essential skill for any system administrator. See you in the next lecture. Welcome back to our exploration of cloud computing foundations. We are beginning a new chapter focused on the mechanisms that allow modern infrastructures to adapt and grow to meet changing technical requirements. In the cloud computing landscape, the ability to manage resources efficiently often determines the long-term success of an application. By mastering scalability and elasticity, you will understand how to design systems that handle massive traffic spikes without manual intervention or excessive costs. We will break down why businesses rely on these automated models to maintain performance while keeping cloud expenditures predictable and aligned with actual usage. This chapter is essential for anyone aiming to pass the LFCA exam and build robust, industry-standard cloud architectures. Scalability refers to the ability of a system to handle increased or decreased workload by adjusting the available resources. We often categorize this into vertical and horizontal scaling, each presenting distinct architectural benefits. Vertical scaling, or scaling up, involves adding more power, such as additional CPU cores or RAM, to an existing server node. This approach is straightforward because you do not need to rewrite your application logic to support multi-node communication. However, vertical scaling is limited by the maximum hardware capacity of the physical host and can lead to significant single points of failure. If the underlying hardware experiences an issue, the application becomes unavailable, making it a design choice that requires careful consideration of uptime requirements. Horizontal scaling, or scaling out, operates on a fundamentally different principle. Instead of making one machine more powerful, you spawn additional nodes to distribute the workload. This strategy is essential for modern web applications that must handle high concurrency. By adding more servers to a cluster, you effectively spread the incoming requests across multiple instances, which significantly improves overall availability. Horizontal scaling inherently supports redundancy. If one node fails, the traffic simply routes to the remaining healthy servers. This requires more complex infrastructure, including load balancing and state management mechanisms to ensure consistency across nodes, but it allows for virtually unlimited growth and fault tolerance. Elasticity takes the concept of scalability a step further by introducing the factor of time and automation. While scaling is the ability to grow, elasticity is the capability to dynamically adjust resources to match demand fluctuations in real time. An elastic system automatically provisions new instances when traffic rises and terminates them when the load subsides. This mechanism, often implemented through auto-scaling groups, allows the system to remain lean during off-peak hours while scaling rapidly during periods of high traffic. By leveraging this, modern applications avoid downtime during unexpected traffic surges while simultaneously preventing the waste of compute resources. The business impact of these automated systems is directly tied to the pay-as-you-go financial model prevalent in public cloud environments. Without elasticity, an organization would be forced to provision permanent infrastructure based on the maximum expected peak load to ensure service availability. This over-provisioning leads to significant capital waste during nights, weekends, or any time usage falls below that peak threshold. Conversely, an elastic model ensures that your infrastructure investment tracks closely with your actual utilization patterns. Automating this adjustment process enables teams to shift their focus from capacity planning to application development, while financial departments benefit from more accurate, consumption-based budgeting. Handling peak loads through these methods effectively reduces the spillover that often results in system crashes on traditional hardware. By distributing traffic during massive influxes of users, applications remain responsive and capable of completing transactions. The orchestration layers managed by cloud providers handle the complexity of spinning up new virtual machines or containers based on predefined triggers like CPU percentage or memory usage. Once the traffic volume decreases below a certain threshold, the orchestrator systematically scales down, ensuring that overhead remains minimal. This constant cycle of expansion and contraction is the hallmark of modern, resilient web architecture. I look forward to discussing how these systems maintain high availability in the next session. Welcome back. Today, we are exploring the architecture of high availability and how load balancing ensures that our services remain online despite underlying hardware failures. This domain is critical for anyone managing production systems where downtime results in significant operational costs. In the context of modern infrastructure, high availability is not merely a goal, but a requirement for any service expected to provide consistent uptime. We measure this through service level agreements, or SLAs, which define the expected percentage of availability, often expressed as a series of nines. Achieving 99.999% availability, frequently referred to as five nines, requires a rigorous approach to eliminating every single point of failure. If your application relies on a single server, that machine represents a bottleneck that, when downed, halts your entire service. By introducing redundancy at every layer, we transition from fragile configurations to robust architectures capable of weathering hardware degradation and localized outages. This involves moving beyond a single server or data center to a multi-zone or multi-region deployment strategy. Load balancing serves as the traffic controller in this resilient equilibrium by distributing incoming requests across a pool of backend servers. Rather than directing all users to one node, an entry point like Nginx or a proxy accepts the connection and delegates the workload according to defined algorithms. You might use round robin to treat every server equally, or weighted least connections if some nodes possess more processing power than others. If one server becomes unresponsive, the load balancer identifies this failure through continuous health checks and silently routes traffic to the surviving members of the cluster. This mechanism ensures that users experience continuity even when the backend infrastructure undergoes maintenance or experiences unexpected hardware faults. Understanding how these layers interact is core to mastering high availability in a cloud-native or virtualized environment. Failover mechanisms and data replication are the gears that keep the engine turning when a primary component meets its end. Active-passive setups keep a standby server ready to assume the identity and workload of a failed primary, while active-active configurations utilize all resources simultaneously to maximize performance. However, keeping the application stateless is often the most effective way to simplify this process, as it allows any server to handle any request without needing local session data. Beneath the application layer, database replication becomes the primary complexity, as data must be kept consistent across multiple geographic regions. Using synchronous replication guarantees consistency at the cost of latency, whereas asynchronous replication favors speed but presents a risk of data loss during a sudden crash. Balancing these trade-offs is where architectural design meets reality, and choosing the right strategy depends entirely on the requirements of your specific workload. Business continuity is built upon the assumption that failure is inevitable, and that our systems must be prepared to absorb that impact gracefully. By distributing instances across physically separate availability zones, we protect our services from localized events like power outages or network fabric failures in a specific rack. If an entire region experiences volatility, having a secondary region configured with automated failover allows us to shift traffic and maintain the defined SLA. While this increases the complexity of our deployment pipeline, the investment pays dividends through increased reliability and trust. When you approach the exam, think of high availability as a holistic discipline that encompasses hardware, software, and the network fabric connecting them. Familiarity with these patterns enables you to design systems that are not just functioning, but reliable under pressure. I will see you in the next lecture. Welcome to this section on cloud infrastructure, where we will demystify how data lives and travels in the cloud. We're going to explore storage architectures, network isolation, and the mechanisms that keep your distributed applications performing optimally. When we interact with cloud storage, we typically categorize our requirements into block, file, or object storage, each serving distinct operational needs. Block storage acts like a raw hard drive attached to a virtual machine, providing high performance for databases or boot volumes where low latency and random input-output access are critical. Because the operating system manages the file system on top of these blocks, it remains highly flexible, though it is generally restricted to a single instance connection. In contrast, file storage provides a hierarchical structure that can be shared across multiple instances simultaneously, utilizing protocols such as NFS or CIFS. This makes it ideal for shared content repositories or development environments where multiple servers need access to a common dataset. Object storage, however, operates differently by managing data as discrete objects contained within buckets, identifying them by unique keys rather than file paths. This approach is highly scalable and cost-effective for static media, backups, or large-scale data analysis, because you typically access these objects over HTTP or API calls rather than mounting a drive. Moving beyond storage, the architecture of cloud networking relies heavily on the concept of a virtual private cloud, which provides a logically isolated section of the cloud provider's network. Within this virtual private cloud, you divide your address space into subnets, which are smaller, segmented network ranges that group resources based on security requirements or function. To manage traffic flow, we use internet gateways to act as the bridge between your private network and the external public internet, allowing your services to communicate with the outside world. Security groups function as virtual firewalls attached to the network interface level, enforcing ingress and egress rules that determine exactly what kind of traffic is permitted to reach a specific instance. By carefully applying stateful rules here, you ensure that only legitimate requests can access your application endpoints, effectively shielding your internal resources from unauthorized access attempts. These components form the foundation of a robust, secure infrastructure design in any major public cloud environment. To ensure global delivery at scale, cloud providers utilize content delivery networks, which consist of a geographically distributed group of servers that cache content closer to the end user. By placing copies of your static files at edge locations, you significantly reduce network latency because the data does not have to be retrieved from the origin server every single time a request occurs. This setup does more than improve user experience. It offloads a substantial amount of traffic from your primary service infrastructure, thereby improving the overall throughput capacity for your dynamic enterprise applications. When we consider the interconnected nature of these services, it becomes clear that resource dependencies are a major factor in performance bottlenecks. If a web application relies on a database in one region and a static file store in another, the round-trip delay adds up quickly, which is why network architecture must be planned with geographical affinity and dependency chains in mind. See you in the next lesson. Welcome to our exploration of serverless architecture, where we shift focus from managing virtual machines to executing logic on demand. In this chapter, you will master the principles of event-driven design and learn how to optimize cloud costs through function-as-a-service deployments. Serverless computing represents a paradigm shift in how we approach infrastructure, as it abstracts away the underlying server management entirely. When you adopt the serverless model, the cloud provider takes over the responsibility for provisioning, scaling, and maintaining the infrastructure required to run your code. This means your operational overhead drops significantly because you no longer need to patch operating systems, manage kernel updates, or worry about long-term capacity planning. Instead, you focus purely on writing the specific code or business logic that delivers value to your users. Popular implementations such as AWS Lambda or Google Cloud Functions exemplify this approach by allowing you to define a single function that executes in response to specific triggers. Because the environment is ephemeral and managed for you, you can deploy features faster and with less configuration clutter. It is a powerful abstraction that allows developers to treat infrastructure as a transient necessity rather than a permanent home for their applications. At the heart of serverless computing lies the event-driven architecture, a design pattern where the execution of code is triggered by predefined events. These events can take many forms, including an HTTP request arriving at an API endpoint, a file being uploaded to cloud storage, or a message appearing in a queue. When the provider detects the designated event, it quickly spins up a runtime environment to execute your function and then tears it down once the task is complete. This mechanism directly enables the benefit of zero idle time costs, which is a significant economic advantage for many enterprise use cases. In a traditional virtual machine setup, you pay for the instance to run 24/7 regardless of whether it is processing traffic or sitting idle waiting for requests. With a serverless function, if no events occur during a given hour, your cost for that duration is effectively zero. This granular billing model aligns your infrastructure expenses perfectly with your actual utilization patterns rather than your projected capacity needs. Determining when to use serverless versus permanent virtual machine instances requires a careful analysis of your application's workload characteristics and predictability. Serverless is often the superior choice for functions that exhibit bursty or irregular traffic patterns, such as processing logs, performing on-the-fly data transformations, or powering backend APIs. Because these types of operations can happen unpredictably, maintaining a cluster of virtual machines to handle potential peaks is often an inefficient use of resources. Conversely, if your application requires a constant, steady stream of throughput, a permanent instance might prove more cost-effective over the long term. You might find that the startup latency inherent in serverless, sometimes called a cold start, could negatively impact your performance requirements for certain high-frequency workloads. Thus, the decision resides in balancing the flexibility and automatic scaling of serverless against the consistent performance and control offered by traditional virtualized infrastructures. Considering these factors, it is easy to see why serverless functions are the go-to solution for asynchronous tasks like image resizing after a user upload or periodic database cleanup routines. These hands-free operations illustrate the true beauty of offloading the heavy lifting to the cloud provider, as the platform automatically scales instances to accommodate input volume. If your function suddenly needs to process thousands of events simultaneously due to a spike in user activity, the cloud provider manages that concurrency without your input. You do not need to rewrite your application to handle multi-threading or complex load balancing configurations, as the infrastructure layer handles that complexity on your behalf. This reduction in technical debt allows teams to iterate rapidly, testing new features in production without the fear of cascading infrastructure failures. Ultimately, serverless is less about the technical novelty and more about aligning your operational strategy with the actual demand of your software systems. I will see you in the next lecture. Welcome to our exploration of infrastructure as code, a paradigm shift that fundamentally changes how we manage modern computing environments. In this chapter, we will master the art of defining server configurations through declarative text files rather than manual procedures. Infrastructure as code, or EEC, is essentially the practice of managing and provisioning computing infrastructure through machine-readable definition files, rather than physical hardware configuration or interactive configuration tools. When we treat infrastructure as code, we are applying the same rigor to server environments that we apply to our software source code. This means that instead of manually configuring a web server by logging in and installing packages, we write a text file that declares the desired state of that server. Because this configuration exists as a file, it can be tracked, versioned, and audited with the exact same tools we use for application development. By moving away from manual setup, we eliminate the human error inherent in repetitive, click-heavy administrative tasks that so often lead to reliability gaps. This shift allows us to move from an imperative mindset, where we describe the steps to change a system, to a declarative mindset, where we describe the final outcome we intend to achieve. The primary benefit of this approach is reproducibility, which ensures that your development, testing, and production environments are functionally identical. Without EEC, teams often struggle with the problem of configuration drift, where environments slowly diverge over time due to undocumented manual changes, patches, or updates. If you have ever encountered a bug that only appears in production because the test server was missing a specific library version, you have experienced the consequences of drift. By using an EEC tool, you define the stack in code, store it in version control, and redeploy it to any environment with total confidence. This consistency is the backbone of efficient DevOps workflows, as it enables teams to spin up complete architectural stacks in minutes rather than days. It transforms the deployment process into a repeatable, automated operation that scales horizontally across as many regions or environments as the business requires. To implement this vision, you must familiarize yourself with the prominent tools that act as the execution engines for your infrastructure definitions. Terraform is perhaps the most widely recognized tool in the space, functioning as an infrastructure orchestrator that uses its own domain-specific language to provision resources across various cloud providers simultaneously. Ansible, by contrast, focuses heavily on configuration management and application deployment, leveraging human-readable YAML files to push changes to existing servers via SSH. Meanwhile, CloudFormation serves as the native infrastructure management service for the AWS ecosystem, using JSON or YAML templates to model and deploy collections of related resources. While these tools differ in their underlying implementation and scope, They all share the fundamental design of consuming a formal text specification to orchestrate complex cloud architectures. Learning these tools requires you to understand the declaration of resources, the management of dependencies between those resources, and the evaluation of the execution plan before you apply your changes to a live environment. Transitioning to EEC does not mean your existing skills in Linux administration are obsolete, but rather that those skills are now packaged and deployed at scale. When you write an Ansible playbook to manage users or a Terraform module to provision a virtual machine, you are relying on your foundational knowledge of how Linux systems operate, how permissions function, and how packages are managed. By abstracting these tasks into code, you are merely automating the manual process of executing commands on a remote terminal. This ensures that the entirety of your system's lifecycle is documented, peer-reviewed, and maintainable by anyone on your team with the appropriate access. Embracing this methodology is essential for any IT professional looking to thrive in cloud-native environments where agility and stability remain the most important performance metrics. I look forward to our next session. Welcome back to our journey through the networking landscape. In this lesson, we will begin our exploration of the OSI and TCP IP models, which serve as the fundamental blueprints for how data traverses our networks. The Open Systems Interconnection Model, or OSI model, is a theoretical framework that breaks down network communication into 7 distinct layers to promote interoperability between heterogeneous systems. Starting from the bottom, the physical layer manages the raw bitstream transmission over physical media, such as cables or wireless signals, while the data link layer ensures reliable data transfer between adjacent nodes by handling frames and physical addressing. Moving up, the network layer is responsible for logical addressing and routing, which is where protocols like IP operate to determine the best path for data across interconnected networks. The transport layer provides end-to-end communication services, utilizing protocols such as TCP for connection-oriented, reliable delivery, or UDP for connectionless, performance-oriented traffic. Above that, the session layer manages individual communication dialogues. The presentation layer handles data formatting and encryption, and the application layer provides the final interface for network services like HTTP or DNS to interact with user software. You should view these layers as a design abstraction that simplifies complex networking processes by allowing developers to address specific challenges within a discrete functional boundary. Understanding this vertical stack is essential because it provides a consistent vocabulary for diagnosing where a communication fault might reside in a complex distributed system. In practice, the Internet and most modern Linux environments rely on the TCP/IP stack, which consolidates the 7 layers of the OSI model into a more concise 4-layer structure. The network access layer encompasses both the OSI physical and data link layers, focusing strictly on how data frames reach the physical transmission medium, such as an Ethernet interface. The Internet layer maps directly to the OSI network layer, focusing on routing packets across IP networks, while the transport layer maintains parity with its OSI counterpart by managing host-to-host data transfer. Finally, the application layer in TCP/IP absorbs the functions served by the OSI session, presentation, and application layers, acting as the primary interaction point for high-level protocols. When you analyze a network capture, you are essentially observing how protocols like DNS or HTTP wrap their data in segments, then packets, then frames as they descend through these layers. This encapsulation process is a fundamental concept where each layer adds a header containing specific control information, such as port numbers or IP addresses, which the peer layer on the receiving end strips away. By mastering the mapping between these two models, you gain the ability to pinpoint whether a connectivity issue is a physical interface problem at the bottom of the stack or a configuration error in an application-level service. When we discuss the protocol stack, we are rarely looking at a single piece of software, but rather a sequence of operations that maintain the integrity of a message as it traverses a network. Consider the journey of a DNS request. It starts as a query at the application level, is encapsulated into a UDP segment for efficiency, wrapped in an IP packet for routing, and finally framed by Ethernet technology for transmission across a physical wire. This layered architecture allows software developers to write applications that do not need to concern themselves with the mechanical details of physical hardware or packet routing. As a Linux administrator, you will often find that troubleshooting requires you to peel back these layers in reverse, moving from the physical link state up to the specific protocol configuration. When a network service fails, verifying physical connectivity is your first diagnostic step, followed by checking routing tables at the internet layer, and finally examining service logs at the application layer. By consistently applying this systematic approach to network analysis, you remove the guesswork often associated with repairing broken connections. This modularity is not just a convenience, it is the reason that massive global networks can function reliably despite using vastly different hardware components beneath the surface. I will see you in our next technical deep dive. Welcome back. In this session, we will investigate the structural foundations of network communication by demystifying IP addressing and the mechanisms used to organize traffic through subnetting. An IPv4 address consists of 32 bits, typically represented in a dotted decimal notation consisting of 4 octets. Each octet represents 8 bits, allowing a decimal range from 0 to 255 for each segment. Historically, addresses were categorized into classes, such as Class A, B, and C, based on the fixed length of the network and host portions. This classful system proved inefficient because it forced organizations to request large address blocks even when they required far fewer hosts. Consequently, we moved toward classless interdomain routing, or CIDR, which provides a more flexible way to allocate IP addresses using variable length prefixes. Instead of rigid class boundaries, CIDR uses a slash notation to indicate the number of bits allocated to the network portion of the address. This transition is fundamental to how global routing tables remain manageable in the modern internet era. To conserve depleted IPv4 resources, the networking community established clear distinctions between public and private IP ranges. Public addresses are globally reachable and must be unique across the entire internet, which creates scarcity as these addresses are finite. Conversely, private address ranges like those defined in RFC 1918, such as 192.168.0.0/16 or 10.0.0.0.8, are reserved for internal use within local networks and are not routable on the public web. To allow these internal devices to communicate with the outside world, we utilized network address translation, commonly known as NAT. This process maps multiple private internal addresses to one or more public IP addresses at the perimeter of the network. Without NAT, the global depletion of IPv4 addresses would have essentially halted the expansion of internet-connected services years ago. The necessity for IPv6 arose directly from the exhaustion of available IPv4 tuples, which provided only about 4.3 billion unique identifiers. IPv6 expands this address space to 128 bits, utilizing a hexadecimal format that is significantly larger and more robust. These addresses are represented as 8 groups of 4 hexadecimal digits separated by colons, which allows for a near infinite number of devices to be networked globally. Beyond just providing more numbers, the architecture of IPv6 simplifies header processing and improves auto-configuration capabilities compared to the older IPv4 standard. While we still rely heavily on IPv4 in many legacy environments, the industry has been systematically transitioning to IPv6 to support the massive volume of new devices being added to the network daily. Understanding the difference between these two protocols is a critical competency for any systems administrator. Subnetting serves as the logical tool we use to partition a single physical network into smaller, more efficient broadcast domains. By applying a subnet mask, we essentially tell the network hardware which bits of the IP address belong to the network and which belong to the individual host. A typical subnet mask like 255.255.255.0 effectively hides the last 8 bits from the network layer to focus on host identification. This segmentation is crucial for security and performance, as it limits the scope of broadcast traffic and allows administrators to isolate departments within a local area network. For instance, by grouping servers in one subnet and user workstations in another, we can implement distinct routing and firewall policies for different types of traffic. Effective subnetting requires careful planning to ensure that the designated address ranges are large enough for future growth while remaining small enough to minimize unnecessary broadcast congestion. We have covered the architectural requirements for networking segments and addressing. Catch you in the next lecture. Welcome back, as we are now diving into the essential network protocols that keep the internet and your local Linux environments functioning reliably. We will examine how domain names are resolved, how IP addresses are dynamically assigned, and which standard ports you need to monitor to maintain a secure system. When we interact with network services, we rarely type raw IP addresses, as the domain name system acts as a distributed database that translates human-readable domain names into machine-readable addresses. The process begins at the root level, which oversees top-level domains like .com or .org, and then flows down to authoritative name servers that hold the actual records for specific domains. On a Linux machine, the local resolution process is guided primarily by two files that you must understand. The /etc/hosts file acts as a local static lookup table, allowing you to define manual mappings that take precedence over external network queries. Conversely, the s/etc/resolve.conf file is where you instruct your system on which DNS servers to contact for resolving addresses it does not already know. If you ever find yourself unable to resolve host names, these are the two locations where you should instinctively begin your diagnostic process. Managing these settings correctly is a foundational skill for any administrator who needs to ensure reachability across diverse infrastructures. While DNS handles naming, the Dynamic Host Configuration Protocol, or DHCP, provides a mechanism for automatic network configuration, eliminating the need to assign IP addresses manually to every device. When a client joins a network, it broadcasts a request to a DHCP server, which then leases an IP address, a subnet mask, and a gateway address to that client for a predetermined duration. This architectural pattern reduces administrative overhead and prevents address conflicts that frequently occur in environments where administrators rely on static assignment alone. In Linux, DHCP clients are often managed by background services that monitor network interfaces for these broadcast requests. Understanding this handshake is vital because it explains why a network interface might acquire a different address after a reboot or after a lease expiration occurs. Reliable network connectivity usually depends on a stable exchange between your client machine and the local infrastructure managed by such protocols. Beyond address assignment and name resolution, we must consider the protocols that carry our application data, as these are the primary vectors for internal and external machine communication. Web traffic relies predominantly on Hypertext Transfer Protocol, or its encrypted counterpart, HTTPS, which ensures that data transmitted between a client and a server is protected from interception. For file management, the File Transfer Protocol remains a common, albeit insecure, tool for moving data, while Secure Shell is the industry standard for managing remote systems and performing secure file copies. Each of these protocols is associated with a standard registration known as a port number, which acts as a virtual doorway through which traffic enters and exits the machine. HTTP operates on port 80, while its secure sibling HTTPS utilizes port 443 to manage encrypted sessions. Similarly, FTP typically uses port 21 for control signals, while Secure Shell listens on port 22 for administrative logins. Knowing these port numbers is not merely an academic exercise, but a mandatory requirement for configuring firewall rules effectively on your Linux server. If you leave a port open in your firewall configuration without a corresponding service running, you are unnecessarily expanding your system's attack surface. Conversely, if you block a port that is required for a legitimate service like SSH, you will find yourself locked out of your own machine. By mapping these specific protocol behaviors to their assigned ports, you can write precise ingress and egress rules that enforce the principle of least privilege. This practice involves denying all traffic by default and explicitly allowing only the communication channels that are strictly necessary for the server's defined function. A well-hardened system is usually one where the administrator has carefully considered which protocols are truly required and has pinned them to their standard ports with appropriate access controls. See you in the next lecture. Welcome back to our journey through the networking stack. In this chapter, we will master the essential command line utilities required to diagnose and resolve connectivity issues in a Linux environment. When troubleshooting connectivity, the ping command is your most immediate diagnostic tool for verifying host availability. It operates by sending Internet Control Message Protocol echo request packets to a destination and waiting for an echo reply. When you execute a ping command, you are testing basic Layer 3 connectivity between your machine and the target. If the echo requests go unanswered, you might be dealing with a firewall blocking ICMP traffic or a genuine path failure. However, seeing a response confirms that the target is reachable, providing a baseline measurement of round-trip time and packet loss. This tool is foundational because it informs the next steps of your investigation before moving into more granular analysis. Once you establish that a destination is unreachable, the traceroute utility becomes invaluable for path mapping. It identifies every hop that an IP packet takes on its journey across the network infrastructure. By default, traceroute increments the time to live field in the IP header of each outgoing packet to force routers along the path to send back error messages. This essentially provides a geographical or structural map of the network nodes between you and the target host. Understanding these hops allows you to pinpoint exactly where traffic is being dropped or significantly delayed. It transforms a vague connectivity issue into a concrete problem located at a specific intermediate gateway or service provider switch. Managing network interfaces requires a clear understanding of the tools available, specifically comparing the legacy ifconfig with the modern IP command. While ifconfig has served for decades as the standard for checking IP configuration and interface status, it is officially deprecated in most modern distributions. The IP command from the iProut2 suite provides a much more robust framework for managing routes, devices, and tunnels. Using IPADR allows you to view detailed information about current IP addresses and interface operational states with much greater efficiency and clarity. Transitioning to these modern tools is not just a matter of preference, but a necessity for working on contemporary Linux kernels. To gain insight into the network services running on your system, you must inspect listening ports and establish connections using netstat or SS. The SS utility is the successor to netstat and is significantly faster because it fetches information directly from kernel space. When you run these utilities, you are essentially asking the kernel to list which sockets are currently open, their associated protocols, and the processes owning them. This is critical for identifying whether a web server or database is properly bound to its assigned port and listening for incoming connections. If a service is configured to start but fails to bind to its port, these utilities will immediately reveal the underlying bind failure. DNS resolution is a frequent point of failure, and the dig and host utilities are essential for debugging these name resolution issues. While host provides a straightforward and quick way to map domain names to IP addresses, dig offers far more detailed information about the query process. By examining the authority section or the additional records in a dig response, you can determine how your recursive resolver is failing to find a specific record. If one domain fails to resolve while others succeed, you might be looking at a stale TTL or a misconfigured authoritative name server. These tools allow you to bypass system libraries and verify exactly how the DNS infrastructure is responding to your queries. Finally, the curl utility serves as a powerful instrument for verifying web services and identifying bottlenecks during primary system diagnostics. Unlike basic status checkers, curl excels because it can output the timing information for various stages of the HTTP request, such as connection time, time to the first byte, and total transfer time. This granular breakdown of the request lifecycle helps you determine if a site's slowness is due to a slow handshake, high latency, or heavy payload delivery. Identifying whether the delay resides in the network layer or the application server itself is a diagnostic skill that separates efficient troubleshooting from blind guessing. Utilizing these metrics allows you to provide a data-driven assessment of network health without relying on anecdotes or guesswork. I will see you in the next lecture. Welcome to this chapter on security fundamentals. In this module, we will explore the foundational principles that govern how we protect information systems and secure data within modern environments. If you have ever looked at the professional landscape of IT security, you have almost certainly encountered the CIA Triad. This conceptual model, consisting of confidentiality, integrity, and availability, serves as the bedrock upon which all organizational security policies are built. When we discuss confidentiality, we are primarily concerned with ensuring that sensitive information is accessible only to those authorized to view it. This requires rigorous access controls and encryption techniques aimed at preventing data breaches and unauthorized disclosures. Integrity, by contrast, focuses on the accuracy and trustworthiness of the data throughout its entire life cycle. It guarantees that information is not tampered with, altered, or corrupted, whether accidentally or maliciously, ensuring users can rely on the systems they interact with. Finally, availability ensures that information and resources are accessible when required by authorized users, which involves maintaining stable hardware, optimized software, and sufficient network capacity. Balancing these three components is not always straightforward, as security measures sometimes conflict with the ease of system access. To implement these theoretical principles effectively, we must adopt concrete strategies, such as the principle of least privilege, or POP. This principle mandates that users and processes should only be granted the minimum level of access necessary to perform their required tasks. By restricting privileges in this way, we inherently limit the potential blast radius should a user account or application be compromised by an attacker. For instance, a basic user should not hold administrative rights for system configuration changes, just as a read-only logging service should not have write access to critical application directories. Integrating this approach with multi-factor authentication, known as MFA, adds a vital layer of defense by requiring multiple proofs of identity before access is granted. MFA significantly reduces the risks associated with compromised passwords, which remain a leading cause of data breaches in corporate infrastructures. When we layer these controls, we build a defense-in-depth strategy where the failure of a single security measure does not lead to a total compromise of the system. Beyond technical controls, it is necessary to view security through the lens of a risk management lifecycle. No system can ever be perfectly secure, so the goal shifts toward identifying, assessing, and mitigating risks to acceptable levels throughout the operation of your infrastructure. This lifecycle involves continuous monitoring of systems to detect anomalies that might signal a security threat, followed by rapid incident response to contain damage if a breach occurs. In a practical Linux environment, this involves auditing user actions, reviewing system logs to detect unauthorized access attempts, and maintaining software that is free of known vulnerabilities. Understanding these concepts is not just about passing an exam, but about developing the mindset required to maintain a secure server environment. As systems increase in complexity, maintaining the integrity and availability of data becomes a standard part of day-to-day administration rather than an afterthought applied at the end of the development pipeline. Every decision you make as an administrator should be filtered through these core principles to ensure that system stability and data protection remain the primary focus. I look forward to discussing the practical applications of these concepts in our next session. Welcome back. We are now entering the chapter dedicated to encryption and PKI basics, where we will demystify how data remains secure and private in transit. This section ensures you gain the critical knowledge required to master modern security standards and pass your certification exam with absolute confidence. To understand data security, we must first distinguish between symmetric and asymmetric encryption. Symmetric encryption utilizes a single secret key that both the sender and the receiver possess to encrypt and decrypt information, which makes it computationally efficient and ideal for bulk data transfer. Because the same key is used for both operations, it introduces the logistical challenge of secure key distribution without the key being intercepted by unauthorized parties. Asymmetric encryption, or public key cryptography, solves this by employing a mathematically related pair of keys consisting of a public key and a private key. The public key is widely distributed to anyone who intends to send encrypted messages, whereas the private key is held strictly by the owner and remains confidential. Data encrypted with a specific public key can only be decrypted by its corresponding private key, effectively ensuring that even if the public key is exposed, the integrity and confidentiality of the message remains secure during communication. This architecture forms the backbone of secure digital interactions across the internet. Data integrity is an equally vital component of cybersecurity, which is where hashing algorithms prove their worth by providing a digital fingerprint for files. A hash function takes an arbitrary amount of input data and produces a fixed-size string of characters that represents that content, ensuring that even a one-bit change in the original file results in a completely different output. Tools such as MD5-SUM and SHA-256-SUM are standard utilities in the Linux environment that allow users to generate these checksums for verification purposes. When you download a software package, comparing the provided hash against the hash you generate locally confirms that the file has not been altered or corrupted during the download process. While MD5 is often used for quick checksums, it is cryptographically broken and should never be used for security-critical tasks involving sensitive data. Conversely, SHA-256 remains the current industry standard due to its robust resistance against collision attacks, making it the preferred choice for verifying the integrity of sensitive system files and downloaded binaries. Public Key Infrastructure, or PKI, is a hierarchical framework that utilizes digital certificates to establish trust across inherently untrusted networks like the Internet. At the heart of this system is the Certificate Authority, a trusted third-party organization that authenticates the identities of entities and binds them to their public keys. When you visit a website protected by SSL or TLS, the server presents a digital certificate that has been digitally signed by a trusted CA, effectively vouching for the server's identity. The browser maintains a store of root certificates from known, trusted CAs, allowing it to verify the chain of trust from the website all the way back to a root that the operating system inherently trusts. This PKI mechanism is exactly what prevents man-in-the-middle attacks, where an imposter might otherwise attempt to intercept your connection. By providing a standardized structure for identity verification, PKI allows for secure electronic commerce and private communications. The proliferation of TLS is what ultimately secures the vast majority of web traffic, building upon the foundations of PKI to provide encryption, authentication, and integrity simultaneously. When a TLS handshake initiates, the client and server negotiate a suite of cryptographic algorithms and exchange public keys to establish a shared session key, switching to symmetric encryption for the remainder of the session to maximize performance. This process ensures that eavesdroppers observing the network packets cannot decrypt the content, even if they manage to intercept the transmission. Digital certificates are not just static markers of identity, but are time-sensitive documents that include expiration dates and revocation information to keep the ecosystem resilient against compromised keys. By understanding the role of your system's certificate store and the necessity of certificate validation, you can properly secure your services and protect data against modern network threats. As a Linux administrator, managing these certificate chains and understanding the underlying cryptographic logic is a foundational requirement for maintaining a secure and professional cloud infrastructure. Good luck with your ongoing studies, and I will see you in the next lecture. Welcome back. Let us discuss how to harden and effectively manage secure shell access to your Linux systems. When we handle remote administration, we must pivot away from inherently insecure clear text protocols like Telnet, because they expose credentials and sensitive data to anybody intercepting the network traffic. Secure Shell, or SSH, serves as our primary defense by providing a cryptographically secure channel for command line access. The default configuration of an SSH daemon is often convenient, but rarely sufficient for production environments or exposed servers. We start our hardening process by addressing the default settings that attackers scan for immediately upon targeting a new system. By modifying the default port 22 to a non-standard port in the configuration file, we can reduce the volume of automated script kiddie login attempts hitting our infrastructure. While this is security through obscurity, in the context of global scanning, it effectively keeps your logs cleaner and your administrative overhead lower. Disabling root login is a fundamental policy that you must implement on every server you manage. By setting the permit root login directive to no within the sse.config file, we force administrators to authenticate as a standard user first, and then elevate privileges using utilities like sudo. This creates an audit trail that distinctly links actions to specific user accounts rather than a shared, powerful superuser identity. Furthermore, moving away from password-only authentication is non-negotiable in modern infrastructure management. We replace passwords with public key cryptography, where the client holds a private key and the server trusts a corresponding public key. This approach is not only immune to standard brute force dictionary attacks, but also significantly more ergonomic when managing several different servers. To implement key-based authentication, you generate an RSA or ED 25519 key pair on your local machine and copy the public portion into the authorized AGIRS file on your remote server. This file acts as a gatekeeper, and the permissions on it must be strictly set so that only the owner can read or write to it. If the global or user-specific SSH directory has incorrect permissions, the SSH daemon will often refuse to operate to protect you from your own configuration mistakes. Concurrently, your local client uses a known hosts file to store the identity fingerprints of servers you have connected to previously. This mechanism prevents man-in-the-middle attacks by warning you if the server's identity signature changes unexpectedly during a connection attempt. Always verify these fingerprints upon your initial connection to a new host to ensure you are connecting to the legitimate target. Managing complex connection strings for dozens of servers becomes tedious, yet we can simplify this dramatically with the SSH configuration file located in the .ssh directory on your local machine. By defining host aliases, you can turn a long, repetitive command involving specific usernames, IP addresses, and identity files into a simple shorthand. Instead of typing the full string every time, your configuration maps these parameters to a single identifier, making daily administrative tasks fluid and less error-prone. This configuration does more than just save keystrokes. It encourages consistent server management practices across your entire team. You can define specific forwardings or heartbeat intervals within these aliases to keep connections stable during long sessions. Beyond simple login management, SSH is an incredibly powerful tool for tunneling other, less secure protocols through an encrypted pipe. When an application requires a service that lacks native encryption, we can map a local port to a remote service through an SSH tunnel. This encapsulates the raw data packet inside the encrypted SSH stream, effectively protecting it from packet sniffing regardless of the underlying network security. The utility of this pattern extends to remote database management, web administration consoles, or legacy management interfaces that would otherwise be unsafe to expose directly. By mastering these SSH fundamentals, you transition from being a passive user of the terminal to an active architect of secure remote access. I will see you in the next lecture. Welcome back. In this lesson, we will explore the mechanisms that protect a Linux host from unauthorized access and brute force threats. Local security begins with the concept of least privilege, which you should apply not just to users, but to the network traffic reaching your machine. Managing incoming and outgoing traffic is traditionally handled by filtering tools like IIPtables or the more modern front-end Firewalled. While IIPtables operates at a lower level by manipulating net filter hooks inside the Linux kernel, Firewalled introduces the concept of zones and services to simplify complex rule management. A zone defines the trust level for a specific network interface, and by assigning a NIC to the public zone, you can effectively block all unsolicited inbound traffic by default. This approach ensures that if a service is not explicitly allowed via a service definition or port rule, the firewall drops the packet silently. Understanding this distinction is vital because misconfigured rules often lead to either complete isolation or, worse, an overly permissive system that exposes vulnerable internal services to the public internet. Beyond network boundaries, we must consider the integrity of the file system and processes through mandatory access control systems like Linux or AppArmor. Unlike traditional discretionary access control, where file ownership dictates access, these systems label every process and file with a specific security context. Linux, for example, enforces a policy that prevents a compromised web server process from reading your shadow file, even if the process is running as a highly privileged user. This provides a robust layer of defense and depth, effectively containing potential breaches to the specific service that was compromised. AppArmor achieves a similar goal, but relies on profiles based on file paths rather than kernel-level labels, which some administrators find easier to maintain in specific environments. Regardless of the choice, these frameworks are essential in modern Linux distribution security because they mitigate the risks associated with vulnerable applications. Securing user authentication is another pillar of local defense, and this is where pluggable authentication modules, or PAM, become indispensable. PAM allows system administrators to define requirements for password complexity, lockout policies, and even multi-factor authentication without modifying the actual application code. By editing specific PAM configuration files, you can enforce length, character diversity, and even dictionary checks to ensure users create robust credentials. These modules intercept the authentication request and validate the proposed password against your defined security policy before allowing access to the system. While this does not prevent an attacker from attempting to guess a password, it significantly narrows the viable attack surface by making common or weak passwords unusable. Properly configured PAM modules act as the first gatekeeper, enforcing organizational security standards programmatically and consistently across all local accounts. Finally, we must address the reality of automated brute force attacks that target reachable services like SSH by constantly attempting to guess login credentials. Fail2ban is a powerful tool designed to mitigate this threat by constantly scanning system logs, such as the authentication log, for patterns of repeated failed attempts. When an intruder crosses a defined threshold of failures within a specified time window, Fail2ban automatically updates the firewall to drop traffic from that source IP address for a set period. This proactive response effectively silences attackers before they can succeed, preserving system resources and preventing unauthorized account takeover. You should view Fail2ban not as a replacement for strong passwords or SSH key-based authentication, but as a necessary dynamic shield against the high-volume automated scanning that occurs on any network-connected Linux host. It bridges the gap between static firewall rules and the dynamic nature of persistent credential harvesting attempts. See you in our upcoming session. Welcome back. In this final session, we will synthesize our knowledge across all major Linux certification subdomains and exam objectives to ensure you are fully prepared for the assessment. Reflecting on the breadth of the Linux Foundation Certified Associate objectives, it becomes clear that success depends on more than just rote memorization of command flags. We have navigated the Linux file system hierarchy, mastered essential shell navigation, and transitioned into the complexities of system administration. Administrators must intuitively understand how to manage software packages using tools like apt or yum, while simultaneously maintaining secure oversight of user and group permissions. By decoupling these individual tasks, we see a pattern where the Linux kernel and its user space utilities function as a cohesive whole. Whether you are inspecting the boot process via systemd or monitoring active processes, your goal remains providing a stable environment for applications to thrive in. Now is the time to verify that you can articulate these concepts not as isolated facts, but as an integrated toolkit for modern operations. The shift toward cloud infrastructure and virtualization adds another layer of complexity that you must now internalize as a core competency. We examined how cloud delivery models and containerization differ from traditional hardware-bound virtual machines, forming the backbone of modern scalability. Understanding high availability, load balancing, and the nuances of cloud storage is no longer optional for a systems professional. Simultaneously, you must remain proficient in software development lifecycles, such as the iterative nature of Agile versus the linear progression of Waterfall. Proficiency in Git for version control is a non-negotiable skill when working in distributed teams or infrastructure as code environments. When you approach the exam, view these methodologies through the lens of efficiency and reliability, as that is how they are intended to function in a production ecosystem. Networking and security foundational knowledge ties your Linux administration skills to the broader technological landscape. We have dissected the OSI and TCP IP models to understand how data encapsulates and traverses physical and logical boundaries. Your ability to troubleshoot connectivity using standard utilities and secure remote access through SSH is critical for the exam and your professional longevity. Remember the CIA Triad: confidentiality, integrity, and availability, because it serves as the ultimate benchmark for every security policy you implement. From firewall configuration to the management of encryption keys within PKI, these security tasks ensure the system remains resilient against unauthorized access. If you can explain why a specific protocol choice or permission setting directly supports one of these three pillars, you are well positioned for the upcoming test. As you look beyond this prep course, consider how these building blocks facilitate paths toward more specialized certifications. Pursuing the Linux Foundation Certified Engineer or the Certified Kubernetes Administrator exams requires that you already possess the rock-solid foundation we have established here. Do not rush the transition. Instead, focus on practicing these commands in a lab environment until they become second nature. The LFCA is designed to test your ability to think critically about system configuration, security, and cloud interoperability. Read every question carefully during the exam to identify the underlying administrative challenge before selecting the most efficient solution. You have invested the time to understand the theory, and now you must apply that knowledge with tactical precision. I wish you the best of luck on your exam.